third day in this 1 week FDP, right?
Sir, is a PPT or PDF file, sir?
So this is a PDF file that I am now sharing here. So yes, today we are going to understand the most important concept in machine learning, which is supervised learning, right? So fine, we have already seen in the first session I have introduced to all the participants what is meant by supervised learning. So here today we devote the time, the 2 hours time entirely to this, to the concepts of supervised learning and also the mechanical engineering scenarios that can be modeled using supervised learning algorithms, right? Now these are the things that we are going to cover in today's session. First, we start with the definition of supervised learning. Then we understand the basic concepts which are most important for which acts as building blocks to understand this entire supervised learning topic. And then we see the applications relevant to mechanical engineering. And then we will go through the regression as well as classification algorithms, some of the regression and classification algorithms for mechanical engineering scenarios, right? So see here, yes, this image is well known to us, which we have already covered in the first day. So there are different types of machine learning. Here it is shown only three. That what we have covered the fourth type of machine learning also. What are those? The first one is supervised learning. Second is unsupervised learning. Third we have seen is semi-supervised learning, and the fourth is reinforcement learning. Right now we are concentrating on the supervised learning form of machine learning, right? So now the definition is like this: what is meant by supervised learning, right? So if you observe the definition itself is saying it is a kind of machine learning where you consider both the input data as well as the output labels, and you provide both of them for the task of learning the models, right? So now what is the supervision in this particular thing? So image, if you see carefully, so see this. So in this image we are providing two pieces of information. The first piece of information are the attributes, right? Attribute 1, attribute 2, attribute 3, and the corresponding data held in that particular attribute column. And also we are providing the output label, which is nothing but class label or target label. All these three are one and the same: target label, output label, or class label, right? So we are providing these two pieces of information to the machine learning algorithm, right? So this machine learning algorithm, what it does is it takes these two pieces of information and induces a model. So if you see carefully here, there are multiple models, multiple instances of the model, right? So that means this is one model, the all this is a second model, and this is a third model. So why so? Why it is possible to have multiple models, right, on the same data, same training portion of the data, that we are going to understand within a few minutes, few seconds or few minutes, let us say. And once you learn a model, once you have the representation of patterns in the form of a model, upon this model what you do is you apply test portion of the data, right? If you see this in in this representation, you see the training portion of the data contains class label information, whereas the test portion of the data contains no class labels, which are to be provided by the model, right? So now when you give test portion of the data to the model, it is nothing but you are applying model onto the test portion of the data, which is nothing but the task of deduction. What you are deducing, what you are generate, what is obtained by applying the model on the test portion of the data, the class label information, right? So here in this entire what you say workflow, which talks about supervised learning, there will be two types of errors. The first type of error is nothing but training error. The second type of error is nothing but test error, right? So we are going to see them in the upcoming slides right now. So is this diagram clear? Right, this is the most important thing. And I would like to confirm, is my voice audible to all the participants?
Yes, sir.
Fine.
Audible.
Okay, thank you. So is this figure clear? Are there any doubts with respect to this figure? Right. So now here theoretically say the test portion of the data does not contain class label information, but in practice what we have is we are generating the test portion of the data from the entire data. This is your actual data. The combination of both training set and test set gives you the entire data, right? So from this you are specifying a percentage upon creating the test portion of the data and the training portion of the data, right? And if you see uh, here in the illustration also, majority of the examples go for training and very less examples or less percentage of examples go for testing here, right? So why we are providing more number of examples for training, why we are using only less number of examples for testing? Because more number of, if you provide more number of examples for training, the algorithm will be able to understand the diverse nature of the present in the data, right? How many different patterns are present in the data, and if it is possible to learn huge number of patterns or more number of patterns from the data, then the generalization capability of the model will increase. So in order to make the model more generic or more general, what is meant by general model or generalization of a model? It means given an unseen instance which is not used for the training during training, the model should be in a position to conclude the class label information. So, and that too, it must be correct. So the model should estimate the correct class label information, right? So how do I say that the model has estimated correct class label information? Is also the concept of evaluating the performance of the classifier or model on the test portion of the data, right? So uh, we are going to understand all these things as part of basic concepts now. So just if you concentrate on this discussion, then it will be easy for you when we go through the various mechanical engineering scenarios under the supervised learning algorithms. Fine. Okay. Now, so this is your formal representation of the supervised learning, which we have already gone through in the first session, but still we need to once again recall or recap this, revise this. See, the formal representation of supervised learning is as follows. So the main aim of this supervised learning is to learn a mapping function from input data to output labels, right? So this is the actual understanding of the supervised learning task. We need to uh, map a function, we need to frame a function, let us say, or identify a function which maps bit from input instances to output labels, right? So this framing or identifying that function is the crucial thing in this particular supervised learning task, right? So this uh, in algorithmic fashion, why we are talking about algorithmic fashion? Because the data is submitted to the algorithm, supervised learning algorithm. So then obviously the algorithm will able to learn only the approximation of the function but not the appropriate function. So these is the important difference between approximate and appropriate function. Approximation of a function deal with the providing estimates, right? Providing estimates of the parameters, whereas the appropriate function will give you the correct estimates, the exact estimates, right? So that's why this supervised learning will concentrate on what is called as the loss function, or what you say, this error function that we are now going to see here, this loss function, right? So assessing the model performance, it is based on the cost function or loss function that you see here. So we talk about that now. So here the training data contains this pair. So as you see, as you have seen from the previous slide, the training data contains attribute data or input parameters. Yesterday I have shared some definitions in the WhatsApp group, in which one of the definition is input parameter. So input parameters are nothing but the input variables from the data set, right? Input variables from the training set. And there is no term called output parameter, rather it is called as output of the model, right? Output of the model is nothing but the class label information, right? So we submit input parameters and output of the label or output of the class to the machine learning algorithm. So the combination of the pair of inputs and the pair containing input and output is nothing but one of the instance in the training data set. As such, if you have more number of examples, this entire thing becomes the training set, instances in the training set, right? Now, and yi is the corresponding class label, right? We know the corresponding class labels, which is nothing but the class label or the target label from the training data, right? The learned model is nothing but hypothesis or model, right? So hypothesis is the approximation or the estimator. We can say it as an estimator in statistics. The model is termed as an estimator. So this estimator should be unbiased estimator, right? So we need to understand that the obtained estimator is an unbiased estimator to provide the coefficients or parameters in the based on the input data, based on the training data, right? So the important point here is, in machine learning, how do you frame this function, right? How do you provide this function, right? Can anybody say, based on the yesterday's discussion, how do we find out a particular function that is suitable for this given task? So based on the yesterday's discussion, anyone please? So some people has someone has asked a doubt, the doubt saying that uh, same training and test sets will be used for different models. So here, for different models, you can have different training and test sets, or you can fix the training and test set and you can form different models. The main important point is, how do you form those different models, right? That is the most important question we are going to address now, right? So the current question is, how do I find out or formulate, or how do I provide the form of the function? So from yesterday's discussion, we could able to learn or understand that if you can visualize the data and understand the structure of the data, then we can come to a basic conclusion that this structure of the data is not is the is actually obtained when you run through for multiple coefficients of a particular function and plot that particular function, right? Only then this kind of what you say visualization, or this kind of the structure, data structure for the data is obtained, right? So for the sake of clarity purposes, I once again what I do is I will go to this one, which is nothing but the expression Desmos expression function calculator. So now I would like to share the screen. 1 minute. 1 minute. So screen share. Right. So this is Desmos graphing. Fine. I will enter into this desmos.com/calculator. So if you want to learn now, you can do so by clicking on this link I am sharing in this chat window. You can also use this. Now I would like to frame my function, right? So the functions I can frame like this, right? X square. So just I kept only x square. Immediately you see what happened. Uh, there is a curve, right? There is a curve. So this is what a quadratic curve passing through origin, right? Quadratic curve
Sir,
passing through.
Santosh sir,
Yes, sir.
make it to full screen, na? I think
This window.
complete window means
Uh,
the view it is not
1 minute. I will try, sir, because this is a web
okay.
page.
Okay. Okay.
I think this I don't know, but 1 minute. So now is it full window, or it is showing as the same?
Okay, sir. You continue, sir.
Right.
No problem.
Okay. So just I have typed x square here. So immediately it is showing me this quadratic curve, right? Passing through origin. Now I will add a what you say, another what you say value, or another variable that is some x, right? Some x. Now you see now the curve is the what is the bottom of the curve is not passing through the origin now. Now it has shifted to the left quadrant, or the negative quadrant. Some what you say, and the bottom of the curve is in the third quadrant now, right? If I am not wrong, it is in the third quadrant. In this third quadrant, the bottom of the curve, if I plot a point, it will give us both x and y values to be negative, right? Now just I will add a simple constant +1, right? Now you see now the curve has shifted to the first and second origins now, right? The curve has been shifted to first and second origin, and the bottom of the curve is in the second origin now, right? So this kind of visualization you can have here, and you can also establish what are called as parameters here, right? So ax square, let us say, and bx, right, plus if you want to have the values of c, so you can establish these slides, right? You can establish these slides, and these slides will will move from -10 to +10 for each of the parameters, right? A, B, and C. And what happens is the curve will actually be animated based on the movement of these particular slides for the or these coefficients, right? So now just I will run the coefficient A. Now you see how the curve is modifying, how the curve is getting animated, you can observe, right? Now I would like to simply run this curve coefficient B, right? You see how the curve is moving, right? So it is dwindling, right, from third origin to fourth origin, and also covering all the four origins right now. So now coming to C, so you see it is going up and down. It will come down now, you see. So you can actually understand the dynamics of the particular equation, and this equation is not a linear equation, it is a quadratic equation, because we started with the x square, right? So automatically it is a quadratic equation, it is not a linear equation. Now how about writing a linear equation, right? We will write a linear equation instead of these all these things. So m into x plus c. So we would like to add coefficients for m, right? M and c. So you see immediately by providing the navigator for both the slope and the coefficient, right? So we have a straight line, right? A straight line is defined for this equation, or for this expression, sorry, for this expression. So now if I move the slide, what is happening? If I move this value m, so now what is happening, you just observe. Now if I simply move this to -1, you see the line has been changed its orientation, its direction, right? So in trend analysis, we simply say if the slope value is negative, that means the trend is downtrend. The trend shown is in the negative direction, or it is downtrend, right? See, if the trend is positive, let us say, it will be in the upward direction, so it is uptrend, right? So like this in trend analysis, just with the help of the sign of the slope, right, we are not at all we are not at all interested in the value of the coefficient or value of the slope, but we are interested in the sign of the slope, right? Accordingly, if the sign of the slope is positive, then we say the line is in the positive upward direction, right? So if the line of this, if the sign of the slope is negative, and then we say the line is in the downward direction in the negative way, right? So now I simply move the C. Now you see this coefficient is moving the straight line, right, in both up and down directions, right? So this is a very important what do you say, coefficient, because in order to make, in order to find out the exact line equation, if you want to find out the exact line equation that fits the training examples, and that clearly classifies both positive and negative examples, fitting this line in a particular location is the crucial one, which is the correct fit, which is the correct location to have the straight line that will linearly separate all the positive and negative examples is important. Yes. Any doubts?
No, sir. Continue. You continue.
Fine, fine. So now this line equation or this line expression is a linear, is in linear form, right? So that's why we are seeing a straight line, right, that is formed here. So somebody has raised the hand. Please unmute yourself and ask the question. Yes,
Sir, I think no doubt. You can continue.
no doubt. Fine, fine. Thank you. So in this manner, what we can do is we can have line equations, line expressions, and we can actually visualize those line expressions. So this kind of visualization, it is possible through exploratory data analysis. So given the data, if you plot the data in the quadrant in the coordinate system, right? So if the data itself is showing this kind of what you say a plot, this kind of plot which shows the data is aligned in the positive x direction in the upward way, then we can say that this data follows a linear form, and we can come to a conclusion that we can use a linear expression for estimating the parameters, right? We can use linear expression for estimating the parameters if the data is plotted in such a way that it forms a non-linear curve in the form of a wave, let us say, in the both upward and downward direction. Based on the structure of the data, we need to finalize the form of the curve or form of the function, and we need to come up with whether it is what is a quadratic expression or whether it is a cubic expression or so on, right? So this particular what you say website is very important to understand the shape of the mathematical expression, right? So then coming to this, now please tell me, is that easy to finalize this expression, if at all, if there is no EDA? And my doubt is to all the participants, if just by plotting the data every time, is it possible to come up with the form of the function? The participants are requested
No,
to
sir. No.
no, right? So it is not possible to actually come up with the right form of the function just by looking at the structure of the data, right? So for more sophisticated and complex machine learning tasks, the machine learning engineer should take the support of domain expert to finalize upon the form of the function. To finalize upon the form of the function. So here, once the form of the function is finalized, then the machine learning algorithm will take this form of the function and estimates the unknown parameters, right, in the form of the function, right? So what are the unknown parameters in the form of the function? So as you have seen in the visualization part, now ax square plus bx plus c, so a, b, c are the unknown parameters which are to be estimated with the help of the input training data, right? So only the machine learning algorithm will only do this thing. Please try to understand, in supervised learning, the algorithm will provide us finally what are the parameters that it has estimated out of training data. So once these estimates are obtained, once these parameter estimates are obtained, what you will do is you will plug in these parameter estimates back into the function, and you apply or you substitute the test portion of the data, so that now the model, right? The estimated form of the function is nothing but the model, right? The estimated form of the function is nothing but the model. Now that model will able to give you the predicted value, right? Give you the predicted value. Did you got my point, all of you? Did any participant has any doubt with respect to this discussion? Okay, fine. So if this is understood, then we need to concentrate on this diagram, and we need to clarify ourselves why these many models have occurred here, right? So what is the reason to see these many number of models, right? So now I would like to answer that. Now if you see, the question is, will a new model gets trained every time by altering the set of hyperparameters? So before understanding this question, first we need to understand what is meant by a hyperparameter, right? So what is meant by hyperparameter? So hyperparameters are those which we tune or which we configure before the start of the training process in the considered machine learning algorithm. In the considered supervised learning algorithm, there will be some set of parameters which are to be tuned beforehand, uh, before you start the training process, right? So we will see what are those hyperparameters with respect to a given machine learning algorithm or supervised learning algorithm in the today's afternoon lab session. So for now, you try to understand in this from this particular slide. These are some of these are no these the listed uh, strings in this particular diagram are the hyperparameters, right? The number of components, the number of folds, right? What the value of eta, the number of iterations, what is the test size, what is the random state value, right? What is the maximum depth of the tree, how many number of nearest neighbors must be there, what is the value of gamma, what is the gamma, what is the value of alpha, right? And so on. Like this, these are to be.
Sir, can you make in the presentation mode?
Yes, yes, sir. 1 minute. Right. So now is this clear, sir, in the presentation mode?
Okay, sir. Okay, go ahead.
Fine. So these are to be set. These are to be set beforehand, before the training actually starts with the help of supervised learning algorithm, considered supervised learning algorithm. So why we should set this? This is the most important question, right? So now these hyperparameters, if you tune, right, you will be able to obtain a model which you would like to have in terms of its performance accuracy, right? So a simple analogy if I take, right, if you are tuning for a particular FM channel, right, if you are tuning for a particular FM channel, earlier we used to have radios, right? Earlier we used to have radios where there are knobs which help us to simply tune to the required station, and this tuning is actually what you say is made this tuning is actually made continuously, right? And this tuning is not done only once and left aside. What you do, you tune once and you check whether you have you are listening to the station correctly or not, right? If there is any noise or if there is noise is present after tuning also, what you do, you come back to the tuning process and you will adjust the knob, right? You will adjust the knob in such a way that once again you are correct you have entered into this particular frequency band, right, of that particular radio FM channel, right? And you do this continuously until you listen to the channel without any noise. Is that right? Right? So the same thing is happening here, right? You come up with some number of hyperparameters initially to form a model, right? To form a model, and you estimate the performance of the model, right? If the performance of the model on the training data is less, what you do is you once again come back and you simply tweak these hyperparameters in terms of values, slightly modify the set of hyperparameters that you have considered for the sake of learning, slightly modify those values, and so once again you go with training, right? And this will give you altogether a new model. Is that right? The earlier model is different, and the current model after tuning these hyperparameters is different, right? So this we need to check iteratively until we form a good set of values, until we find a good set of values for these hyperparameters, which is only understood based on the performance of the model on the training portion of the data, right? So now why we are considering the performance of the model on the training portion of the data? This is the most important point, because you have learned the model with the help of training data, right? You have learned the model with the help of training data, but the model is it is embedded with what is called as irreducible error, right? The model is attached with some amount of error which you cannot replace or which you cannot reduce. Are you getting my point? Right? So 1 minute, please. Yes, sorry for the interruption for that. Now, see, we will continue. We will continue here. So, where are we? We are actually tuning these hyperparameters and forming different models, right? And we are trying to find out the performance of the model based on these tuned hyperparameters, right? So, if the model performance on the test portion of training portion of the data is good, then we finalize this set of values as the finalized hyperparameter values, and we consider that particular model for the further testing, right? So do you have any doubts with respect to these hyperparameters? Right, these are the foundations that we need to learn. For that reason I am going slow. Any doubts? Right, fine. So now these these hyperparameters are set before the learning is actually started. Now then what are these model parameters? What are these model parameters? These are the parameters that are estimated during the training process. This is before the training process we will set, and these are the parameters that are estimated by the algorithm, right? By the algorithm, as we have finalized the form of the function. Now the algorithm is responsible to estimate these parameters, right? What is the parameter here? That is wj, right? This parameter wj is estimated, right, during the learning process, right? So that is the difference between hyperparameter and parameter. This is the most important difference one need to know, right? Now coming back to this answer, now as we have already understood, the question is, will a new model get trained every time by altering the set of hyperparameters? Yes. So every time a new model will get trained, right, by altering the set of hyperparameters, right, in terms of its values. Please try to understand in terms of its values. The most important thing is, right, so hyperparameter tuning is an important step in the machine learning workflow to achieve better model performance. That is what we have discussed now, right? So if you are finalized with the good set of hyperparameters with corresponding values, then the next thing is we are evaluating the performance of the model, that particular model, on the test portion of the data. So obviously we need to be careful in the process of selecting the hyperparameters and finalizing the values for these hyperparameters, right? Now then now the immediate question is, a person who is learning the concept of supervised learning for the first time, so this question might arise. This is a very simple and important question. So by increasing the training data size, will a new model get trained every time? Right? We started with some X number of examples as part of training data, and we have learned a model. Fine, that is good, great. Now, if you are increasing the size of the training data, right? If you are increasing the size of the training data, it doesn't mean that every time you are learning a new model. Rather, your model gets improved with the help of the addition of the data, right? So you see here, increasing the training data size typically refines or enhances the existing model rather than creating entirely a new model, right? This is the most important statement. You are not creating new models every time when you increase the size of the training data. Rather, the existing model gets refined because the algorithm will learn the new patterns, unseen patterns, every time when you add new portion of the data in the training set, right? But in some cases, the most important point is, in some cases, adding more data may not necessarily lead to significant improvements of the model, because if the original data set was already sufficiently diverse and representative, right? That is the most important thing, right? If I take the example of digit recognition data, MNIST digit recognition data, in that we have images, digitized images, which are nothing but the written numbers by so many people, right? So this capture, that particular data set actually captures so much of variation in terms of different shapes, different edges for each digit, right? So if that is the case, then there is no point in improving the size of the data, because the data set itself is huge actually initially. By adding more. Yes, sir. May I request the person to mute the mic? Right. Thank you. So in some cases, just by adding the data is not required, actually not needed, because there are benchmark data sets which actually uh, tells that the data has more diversity and it is more representative. So obviously, when you are using such data sets, you no need to add additional records to that particular set of the data, right? Now, so we are trying to understand supervised learning in two categories: regression algorithms and classification algorithms. So in regression algorithm, we try to estimate a continuous value or predict a continuous value. In classification, we try to classify the incoming unseen example, right, to the discrete classes, available discrete classes from which is already known to the model, right, which is already known to the model, right? So we have example, or what is algorithms falling under these two categories. So before that, so what is the connection between classification and supervised learning that is required? So classification is a specific task under supervised learning, right? It is a specific task under supervised learning. And what we do with classification, we will classify the unseen example with the help of model specified label, right? So I already told you, there is a fine line in terms of understanding the words prediction and classification. So prediction is a word, strictly speaking, prediction is a word you should use when you talk about regression. When you are talking about classification, you should not use the word prediction. Rather, you should use the same word classification for understanding the estimated or the attached class label to the unseen data by the model, right? This is the most important thing. Then, so connection between regression and supervised learning, as I told you, in classification we are classifying the unseen examples to discrete labels, whereas in regression we are predicting the continuous value with the help of historical continuous data, right? So how do we do this for the mechanical engineering scenarios is our prime discussion now, right? So now, continuing with the concepts, basic concepts, here the most important thing is how to check the performance of a model, right? So in regression and these two things, we are talking the definitions of creating a cost function or loss function, in regression, and in classification you are defining the cost function and all other metrics, right? For the sake of understanding the performance of the model on the test portion of the data, right? So earlier we have seen how it is working on the training portion of the data. Model is performing on the training portion of the data, and now we are trying to understand the performance of the model on the unseen portion of the data, which is test portion of the data. So for that, we need to define a function called as loss function or cost function. Both are one and the same. As I told you in the last session, both are one and the same. It is also called as error function, right? But specifically here, they are writing that for regression, we are saying them as these names. We calling with these names. Whereas for classification, we are saying it simply as cost function, right? So now the thing is, the model is to make the model more generalizable. That means, however, whatever data you are submitting, that with the by satisfying the existing features, right, that the model has, without any class label information, it should be able to provide that class label information, right? And that too, it should provide correctly. The label should be provided in the correct fashion by the model, right? If it is providing a wrong label or wrong estimate, wrong prediction, we need to identify that this is a wrong prediction, and we need to come up with a definition called loss function or error function or cost function, and we need to reduce that error, right? We need to reduce this error by optimizing the error function, right? The objective here is to optimize this error function, that is minimizing the error. Which error? Test error. So if it is possible, if you are trying to minimize this test error, then you are indirectly doing what you are doing is you are making the model more generalizable, right? You are making the model more generalizable, right? So any doubts here? Any doubts? Fine. So now what are we doing in order to define this cost
Please
function?
explain once again.
So you would like to have the understanding of in terms of cost function or in terms of definition?
Definition, sir.
Definition. Fine. We'll go back to the definitions. So in terms of classification, the classification means attaching the target label to the unseen portion of the data or test portion of the data with the help of learned model, right? So that attaching the label or providing the label is nothing but classification. The term that we use is classify, right? The task is classification, and what we are doing is we are classifying that particular incoming record with a discrete label, right? Now when it comes to regression, instead of attaching a label to the new record, we are estimating its corresponding continuous value. So if I give an example of estimating the house rent of a particular of a new house, of a particular house, on the basis of earlier seen historical data, earlier seen house rents, right, on the basis of historical data. So what could be the attributes that help to provide the estimation of a house rent? So participants are required to answer this question. What are the attributes of a house that help an individual to estimate the rent of the house?
Area.
Area.
And,
Yes.
area of the house, location.
Yes.
And then the surrounding shops and all those things. And then any schools and malls.
And with respect to house, sir, I am asking with respect to the house. Features with respect to the house.
Features with respect to the house means area,
Area.
and the number of rooms available,
Yes.
then the number of toilets available,
Okay.
and the area of the kitchen,
Yes.
and the arrangement of the rooms, and
Right.
shelves available in the house.
Okay. So all these things, what you are saying, you are absolutely correct, sir. So these attributes, not few of these attributes will play a crucial role in estimating the rent of the house, right? So as you said rightly, the area of the house, and then the number of bedrooms, right? And the number of balconies, right? And also if it differs from person to person, as you said, you said the number of toilets and so on, like this, based on these factors, right? You come to an estimate that for this house, the rent can be this much, not more than that, right? So that kind of estimation you will come, you will have, right? The same kind of estimation can be obtained as a in the form of prediction with the help of regression.
Oh, thank you, sir. Right, sir.
Okay, sir. Okay, sir.
Understood, sir. Right, sir. Thank you, sir.
Right. Thank you. So we'll continue
Santa
here.
sir,
Yes, sir.
Santa sir,
Yes,
some
sir.
answers are in chat box also.
Yes, sir. I am checking. Right, sir. So you can be treated as attributes. Square feet. Yes, yes. This is another right answer. So facilities are how well furnished is the house. Yes. Yes. How well furnished is also one of the attributes, as you say. Carpet area, square feet. Right. Correct. Location, address. Oh, fine. These are the exogenous parameters. Location, space, location, address. Of course, location is an exogenous attribute with respect to the house, right? So we are only concentrating on the what you say feature specific to the house, right? For the sake of estimating the rent, house rent. Fine. Good answers. Good discussions that we are very happy that the participants are very interactive along these 3 days, and we are actually what you say we would like to see the same kind of interaction for the next upcoming 3 days too, so that you will be what you say in the session, your presence will be there in the session, and you will understand the concepts in a more what you say concrete way, right? Fine. Area and square feet and basic amenities, location, right? So that all these things now we have discussed. So fine. So continuing from here, so now as I told you, whatever model that you have learned, that model must be evaluated for its performance on the test portion of the data, right? So it could be a regression model or it could be a classification model. So you should define a cost function or loss function that will provide you the error information, right? Error is nothing but the difference between the actual value and the estimated value. As simple as that, right? So from in the context of classification, the label obtained from the data and the label provided by the model, the difference between the label obtained from the data and the label obtained from the model is an error, right? Or loss. Whereas in regression, it is the real value from the data and the difference between the real value from the data and the estimated value by the regression model. That is nothing but the loss or cost function. So our objective is to reduce this error, minimize this error as much as possible, so as to improve the generalizability of the model, right? Fine. Now, so how these functions are defined, right? You see, absolute error is 1 upon the number of examples, test portion of the size of the test portion, 1 by n into sigma absolute difference between the approximation or hypothesis minus the actual value, right? Minus the actual value. And if you see carefully, for the first two cost functions or error functions are specific to regression, right? whereas the third function is specific to classification, right? A cost function specific to classification, right? So any doubts here? So you can actually encode the labels in order to make the cost function look in similar fashion to the regression function, because if you have the values instead of fail or good and fail, or let us say the outcomes of a gear, outcome of the health status of the gear is good and bad, let us say, are the two values. These are the two values for the status of the gear, condition of the gear, let us say, after manufacturing. Then we can actually encode them into or we can decode them into numbers, right? Or let us say it could be encoder, label encoder. We can, what we are doing is we are mapping a particular label to a particular value 0, one label to a particular value 0, and the other label to a particular value 1, right? If that is the case, then you are simply reducing this number of misclassifications to a particular form of absolute error, or if interested, you can convert it to sum of square errors too, right? All these functions can be interchangeably used, right? Now, so now here the prediction error of any machine learning algorithm can be broken into three parts, right? So error, as I told you, it is the difference between real value and the estimated value. So that error actually internally is decomposed into three parts. The first one is the irreducible error, right? Sigma square is standard deviation, right? Sigma square is variance, right? Or standard deviation. Sigma is standard deviation and sigma square is variance. Is that right? Or what is the correct one? What is sigma square and what is sigma? Square root of variance is standard deviation. So right. So that means sigma square is variance. The variance in terms of error is irreducible, which is already present in the obtained error, right? Which cannot be reduced further. And to this irreducible error, you also have bias and variance, right? So what are these bias and variance? Quickly we go through, right? In the definition itself, you see bias is nothing but the difference between true value and the estimated value. The difference between true value and the estimated value is the bias, right? So somebody please one of the participants
Unmute, Amma.
mute yourself, please. Thank you. Right. Still the sound persists. Okay, fine. Now, bias is the difference between true value and the estimated value, and variance is the difference between, or the variance is nothing but, what is variance? You see, variance is the expected squared deviation around its mean, right? What you are doing, you are calculating the mean of the estimation, and to that mean of the estimation, you are doing the average of the square deviation. So average of the square deviation is nothing but, around its mean is nothing but the variance, right? These in terms of definition, right? These in terms of definition are clearly shown, you see here. Now, why these are added? Why these are present in the error? Why these are present in the error? Why? Because how do you tweak the hyperparameters? How do you tweak the hyperparameters is the most crucial thing. So if you are providing, right, more number of, or high number of values, high parameters, more number of hyperparameters, if you are what is configuring in order to learn a model. My point is, if you are configuring more number of hyperparameters for learning a model, then it results in high bias, right? And then it results in high bias. So high bias is making the model less complex, right? High bias will make the model less complex and variance will be less, right? But the models with high bias are said to be underfitting, right? Underfitting in the sense the training error and the test error both are high, right? The models with high bias will have training error and test error to be high. Our goal is to make the training error and test error of the corresponding model as low as possible, right? So we don't want a high bias model, rather we want a low bias model, right? Now we will understand if the model is low bias, if the model has low bias, then what about its variance, right? Then what about its variance? So whenever a model has low bias, its variance will be high. This is the trade-off. This is the trade-off with respect to bias and variance. The variance is nothing but the error or the difference in terms of the estimate, what is it, the curve, the training error and the test error in terms of distance, right? In terms of distance, right? You see the plot, right? So this variance is introduced by changing the portion of the data for the sake of estimations, right? So it is introduced by having a model that is too sensitive to the fluctuations in the training data, right? So if you simply add a new example, then what is happening? The model performance on the training portion of the data, sometimes it will come to too low or sometimes it goes too high, right? So if the model performance after adding some training data, some additional training data is in terms of error it is high, then we say it is high variance, right? It is high variance. If the error is less, if the variance is less, it means the model is said to be stable by adding new examples also, right? Model is said to be stable by adding new examples also, right? So a high variance can result in the model performing well on training portion but poor on test portion of the data. This is nothing but overfitting, right? Underfitting means a model is performing poor on both training portion and test portion of the data, whereas overfitting is a model is performing good on training portion of the data and performing poorly on the test portion of the data, right? So now how do we address this? This is a what is it, a open challenge till date in machine learning, because any machine learning cannot avoid this, right? You see the figure, you will better understand. If you see this graph, if you see this plot, let us say, so the trainings portion of the data, as the complexity of the model is increasing, right, the error is decreasing. That is what I told you, right? So if you are having if it is high bias and low variance, it means the difference between the test sample and training sample in terms of this distance is till here it is fine, right? From till here it is okay, right? Low bias and low variance we can have. This is the ideal location. This is the ideal location in order to have a good model, right? I can cut off here actually. I can have a cut off pruning, I can prune this and I can stop both training and training and testing at this location on the model, right? Given a model, I can go up to this part and stop the predictions and stop forming the predictions, so that I will have a very good model. Are you understanding my point? So if you have any doubts, please raise the questions, right? So here, that's what this is, nothing but early stopping. Today in deep learning, the term early stopping has come into picture. It says I would like, or the machine learning engineer needs to monitor continuously where the distance is increasing in between training sample and test sample. So if the distance is increasing from a particular point, then terminate forming the predictions and say that the this is my model, and this model is a very good model for estimating the predictions, right? So and this model will give me very less error, right? This model will give me very less error, right? So this region is low bias and low variance region. Now when you are increasing the number of hyperparameters, configuring the number of hyperparameters, you are actually doing what is called as high bias, right? So when there is high bias, automatically the complexity of the model will decrease, right? Sorry, when the complexity of the model is actually increasing, right? When you are increasing high bias, the complexity of the model is increasing. Earlier I said it is complexity is decreasing, but please understand that it is increasing the complexity of the model, right? And variance will be high, sorry, low. Variance will be low. As you are seeing from this, variance will be low. But when you see in this location, when you see in this location, uh, when when the model complexity is increasing to a greater extent, and when you are trying to find the predictions by using test sample with the help of model, what happens is the variance has got increased, right? The distance between these two curves has increased to a greater extent, right? So this distance is increasing. Please try to understand, this distance is increasing. So here we form what we say what is called as high variance, right? So obviously when you are using unseen portion of the data to predict the labels or predict the continuous values, to obtain the continuous values, if the model complexity is high, obviously at this point of time, while predictions, the variance will obtain to be high. So high variance models actually are less biased. They are less biased because the number of hyperparameters that you configure are less, right? So now we need to identify the good fit where we can stop this, and this is the region where you can actually stop learning or stop forming the predictions, stop forming the errors, right? Any doubts here? Fine. So I will continue here now. So that's what I said. There is no escape between bias and variance in machine learning. So increase the bias will decrease the variance. Increasing the variance will decrease the bias, right? So we would like to come up with a particular model that whose behavior is very much required for us to work for both training and testing portions of the data and provide less errors, right? That is what we are trying to find, right? So the values, how do you obtain the performance values? The performance values on the test portion of the data can be obtained by using these techniques like holdout, random subsampling, k-fold cross validation, and confusion matrix. So if you see quickly, if you see holdout means you are already dividing the data into two parts, training part and test part. You are holding out test portion of the data for the sake of training, and once the training has occurred, you are submitting the unseen records to form the what you say predictions or classifications, and estimating the number of misclassifications with the help of loss function, right? Now if you do the same thing for multiple times, this is known as random subsampling. If holdout is performed for many times, then it is called as random subsampling, right? And when it comes to k-fold cross validation, right? When it comes to k-fold cross validation, you see this is the way we do k-fold cross validation, right? This is nothing but leave one out approach, right? So if you see, we have, let us say we have 10 records. Let us say, for example, and in the test portion of the data, we have 10 records, and each record, what you are doing is, in each round, what you are doing is, you are making 9 records to go for training and 1 record for the sake of validation or testing, right? Now you are leaving 1 out and using the remaining 9 for training and using 1 for testing. In round 2, what you are doing, you are taking the second example or second instance, and you are making it as test example and using the remaining 9 examples as training examples, right? So in the same lines here, you are saying based on the user requirement, you can have 5 rounds or 10 rounds, accordingly up to you, right? You are estimating the performance or accuracy of the model like this, right? So 90%, 90%, so on. What you are doing is, in order to obtain the final accuracy, you are doing the average of all the rounds, which will give you the final accuracy of your actual model on the test portion of the data, right? Now, so these metrics we will see over a period of time. These, in the interest of time, I'm skipping these metrics. We'll see in the lab session finally, right? Now the applications relevant to mechanical engineering are shown here. So for the sake of supervised learning, the predictive maintenance, quality control in manufacturing, fault detection and diagnosis, material selection, robotics control, structural health monitoring, and so on. There are remaining many other scenarios or applications from mechanical engineering that you can use in with the help of supervised learning, right? So now we will come into the algorithms and we will understand each of them in a simple way. So there are variety of regression algorithms. Whatever we have shown in the bold form, we will look into them now, right? We are talking about linear regression, multiple regression, and multivariate regression now. So now see here, first coming to linear regression, we all know that it is a data analysis technique or a regression technique which takes into consideration one predictor, right, and one independent variable, right? One dependent variable and one independent variable, right? There will be only one independent variable and there will be one dependent variable. At any point in time, we will have only one dependent variable. Please try to understand, right? We will have only one dependent variable. We can have more than one independent variables. Please try to understand, right? Y is equal to mx plus c, in which y is a dependent variable, x is an independent variable, right? In the same lines, if I have y is equal to ax square, right, plus by plus c, then we have x and y are two independent variables, right? So sorry, z is equal to ax square plus by plus c. We have x and y are two independent variables and z is the dependent variable, right? We can have one or more than one independent variables, but we will have only one dependent variable until we talk about multivariate regression, right? Until we talk about multivariate regression, right? We are trying to find out estimates or the coefficients of the linear regression, right? Now it is of the form like this: y is equal to mx plus b, which we have already seen, right? Y is nothing but the response, x is a predictor, right? So we know what is m and what is b. M is the slope and b is the y-intercept, right? So you would like to find out these m and b values through regression, right? So here, as I told you, we need to find out the values of m and b, and if now after obtaining these values of m and b through linear regression, we plug in back into the actual y is equal to mx plus b, and we will try to we will obtain the predictions, right? We will obtain the predictions, and the difference between the real value from the data and the predicted value can be formed as a loss function, which is expressed in the form of mean square error, right? So this mean square error, or it can be explained in terms of r square also. So this is known as coefficient of determination, If somebody has raised the doubt, raise the hand, please. Please tell me. Please unmute yourself and raise the question. Fine. So I will continue. So here our goal is to have less MSC value. Our goal is to have less MSC value. Now you see here, for the sake of mechanical engineering scenario, we will now understand how to do that. These are the formulae for calculating M and B values with the help of given X and Y values from the data, right? So here the scenario is predicting the length of the machine component based on single feature width of the component, right? If you are given with the values of width, is it possible to predict the length of that particular component? So we can directly do it in Excel, right? Excel, we no need to go with what to say, regression function modeling. So but now we will show you with the in Excel now, right? So quickly we move to the Excel part. 1 minute. Excel, 1 minute. One camera. I think where is camera? Right. I'll show you this Excel. Uh, so we'll share this. 1 minute. Where is this Zoom? Right. So I think this Excel sheet is visible to all of you. You see here, this is the length of the machine component, right? So now we would like to find out the or we would like to predict the new width of the machine component, right? New width of the machine component. So given the length and width values, if I want to predict a new value, new width value for a given length, so how do we do that? Now what you do is, it is quite simple in Excel. We select these two columns, right? And what we do is, we will go to insert and we will plot the line. We will insert the line plot, right? So see here, we have inserted the line plot. So width and length, right? So now if you want to obtain the line equation for this particular two things, right? What you do is, you, or instead of that, you go to a scatter plot. Better you go with a scatter plot, then also it is fine. Insert a scatter plot, right? This is a scatter plot, very meaningful curve here. So you see, the structure of the data is in the increasing fashion, right? Is in the increasing fashion. So this calls for the linear expression, and this is in the straight line form, right? The structure of the data is in the straight line form. So what we can do is, we can plug in the linear equation. We can add the trend line to this data, right? So add trend line. So when I do that, automatically it has added a trend line. You see, it has added a straight line equation. And we can also attach the what you say, function also. You can see what is the equation, line equation, and we can also display the R square value for the data, right? So see here, so this why it has estimated the Microsoft Excel has estimated the values of M and C right? What is the value of M? It is 2.79 and C value is 6.71. And the coefficient of determination R square is 1, which means it is 100%. It is possible to clearly explain the width of the component with the help of length of the component. That is what the meaning of R square is equal to 1, right? So 100% it is possible to explain the width of the component with given the length of the component. That is the meaning, right? Now if I give a new length value, let us say some 24 or 21.56, right? Then can my model able to estimate this value, right? Can my model able to identify this value? So that is what is the thing. Now what I do is, with the help of this function, I would like to find out the values, right? It is y is equal to, this is equal to, let us say this is predicted value, predicted, the predicted, what is this? Width, predicted width. Now what I do is, I will simply use this function, plug this function here, 2.7993 into, in the brackets, what we substitute? This length value, right? This length value B2 plus the value 6.7179, right? The predicted value is, predicted width is like this, you see, right? Is the formula correct? This is B3, B4, 6.79, 2.7993 into X B4. So given the length, we are trying to find out the width, right? Now you calculate the, what you say, error. Now is the line equation same that we got here? We'll check it in the, you see, yes. So predicted length by using the learned simple line equation, right? But if you consider this is your now you see the difference, right? Predicted width and the actual width. The difference is what? Error, cost value. So error,
Check the function.
yes, the check function is
Not
this.
correct.
So this function is, yes, I think this is function after prediction, I think. Is that right? Okay. So what I do is, I'll take only length value.
No, in that formula, I think we have to change the value there. We're taking length.
That's what, sir. What we are trying to substitute here is predict the length of the machine component, right? So that means, okay, so X will become Y and Y will become X, right? Fine, understood. Thank you, sir. Thank you for the update. We need to change the formula. That means this is length value. We're trying to predict the length, right? So this means we are trying to provide the width value, that is A2. Is that right? So A2 and so on. Now is that correct now?
Yes, sir.
Yes.
Now it's right.
Right. Now fine. Now we will calculate the error. Now what is the error? Error is nothing but difference. Is the absolute difference. If you have, you take the absolute difference for each value. ABS of, sorry, ABS of this real value minus C2, the predicted value. What is caps lock? C2. So this is the error.
Not A2, it's B2.
Oh, once again I'm taking
B2
width,
C2.
right? B2 C2, right? I am taking once again width, right? B2 C2, right? Thank you. Right. So this is the error, right? So this is error for each instance, right? This is the error for each instance. Now what is the total error that we have? The total error is, so 1 by, or this entire sum of all these values sum of all these values, right, divided by what is this? What is the count we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18,
20.
19, 20, 21. Right? We have, I think, 20, right? 20. So substitute this value 20. So this is your MSC value, final MSC value, mean square error. Oh, sorry, mean absolute error, MAE. Why? Because we are using only absolute error value, and we have taken average of all those absolute errors to form to get the final MAE, right? If it is square, what you can do is you can take the square of this function, right? Instead of ABS, you can use SQR or square, SQARE. Whichever function is present, you can use that function and you can obtain the square value. So if there is no such function, so any square function, or you can simply go multiply, right? This is equal to this into this, which will give you the same value. Obviously, this returns what? Positive value, right? This returns positive value. So this is squared error, and this is, if you want to do this, you have mean square error. Now this is MSC. Okay, right? Like this, you have formed the error. This error, technically, what we say it as residual, right? So this error plot can also be shown here. So you see, sorry, why it is showing like this? 1 minute. Once again, we go with the data. Yes, error plot is like this. Okay, fine. So this is residual plot, and this residual plot, what you can do is you can have a line onto the residual plot. So if you add the trend line, it will be showing like this. It will be showing like this on the residual plot, which means you can actually identify how much the predicted value is away from the how much the real value is away from the line, right? How much the real value is away from the line, right? Any doubts here? Now what we have done, we have estimated the length of the component with the given the width of the component, right? Now the next one is multiple linear regression. So here, as I told you, in simple linear regression, what we are doing is we are considering only one independent variable and one dependent variable, whereas in multiple linear regression we will have multiple independent variables. You see x1, x2, so on up to xk, and also error term is also added, right? Which will be obvious, which will be natural, right, for representing unobserved factors. So, and this y is your dependent variable, or what you say, predictor. Right, now you see we are trying to predict the efficiency of the heat exchanger based on these parameters. What are these variables? What are those? Flow rate, temperature difference, and surface area, right? Now, how do you estimate the efficiency of heat exchanger in general, right? What the heat exchanger does, what it does? Heat exchanger tries what it does is it transfers the heat from from
Sir,
one
slide
fluid
is
to
not
other
changed.
fluid. Yes,
Slide is not changed.
slide. Yes, 1 minute. I will show you once again. That's what, sir. This is the slide. We are in this slide, right? This output we are seeing this output, right? So the heat gets transferred from one form of the surface to other form of the surface, or one medium to other medium, right? And we can also see the heat exchange, the temperature differences like heat, hot and cool, right? So this kind of heat exchangers are pretty seen in the consumer electronics also, like
Sir, Santosh sir,
refrigerator, right?
Santosh sir,
Sir,
make it to presentation form, na?
fine, right? So heat exchanger devices are there in our consumer in the form of consumer electronics like refrigerator. So where you see the temperature differences present without any disturbances, right? So the fridge is getting cooled and in the front side, and what is actually in the background, the whatever temperature that is getting generated due to external in external factors or internal factors, all that heat is going back, right? And that heat is once again moving in a particular coil, right? And that coil is simply converting that heat to hot to coolness, right? It is converting heat to cool, and that cool what is a gas is once again propagating through the fridge and making the fridge cool, right? So like this heat exchange is actually happening in the fridge. So at that point of time, we have these variables like flow rate, temperature difference, surface area. These are actually the distinguishing factors that are actually helping to predict the efficiency of the heat exchanger, right? So if you plug in the corresponding values in the estimated curve, what happens is you're able to see the predicted values in this fashion, right? For the multiple linear regression plane, right? So now you see this kind of lines are for each value. So if you plot the curve for actual efficiency versus predicted efficiency, we can have multiple lines here, right? But this is not correct to understand. This is the way we will understand, right? Predicted versus actual efficiency, right? So when it comes to multiple independent variables, in order to plot the curve, we need to go with 3D visualization, not with 2D visualization, right? It is not a line anymore, rather it is a plane. So we have three-dimensional data, so we are utilizing plane and axis and 3D visualization to show you how the points are distributed on the plane, right? Now, coming to the multivariate regression, this is different from multiple and linear regression, because in multivariate regression we have multiple independent variables and multiple dependent variables. This is the difference, basic difference between what is a simple normal multiple regression and multivariate regression. So in multiple regression, we have one dependent variable and multiple independent variables. Whereas in multivariate regression, we have multiple independent and multiple dependent variables, right? So the same form of linear expressions or linear equations are provided here, right? In the form of formulations. So y1 is like this and y2 is like this. So for a given scenario, if I consider, so for automotive engine design, now what we are considering is three dependent variables, which is nothing but fuel efficiency, power output, and emissions levels, right? So at any point in time, the emission levels must be low, and the fuel efficiency should be optimized, and power output should be high, right? From an engine. So in order to have the ideal situations in terms of its estimates, so what we are doing is we are considering the corresponding independent variables, which are the most distinguishing variables among all other variables. What are those? The cylinder size, the air fuel ratio, the compression ratio, and ignition timing, right? All these four are the most distinguishing features that help to determine these three dependent variables, the performance of these three variables, right? Now, how do we form mathematical model for this? This is the way we form the mathematical model. These are the independent variables that we are substituting in the equation. Now, the first one is for fuel efficiency, the second is for power output, and third is for emissions, right? So now after substituting the independent variables and expressing in the form of a line equation, we try to do analysis, and that analysis shows the linear regression, or this is ordinal least squares regression. Please try to understand, we are using ordinal least squares regression to estimate the output for each dependent variable. So it is showing us various variables. Our interest is this one, this constant and the other parameters, right? For this function, that is fuel efficiency, or for this equation fuel efficiency. Now for fuel efficiency, the R square value is 86.6, which is pretty good to explain in terms of the fuel efficiency can be explained with the help of these four variables with 86.6% accuracy, right? So in the same lines, for power output, it is possible to explain with 90.4% accuracy why this power output is high with the help of these variables, right? Now in the same lines, it is possible to explain why the emissions are less with 86.4% accuracy with the help of these four input parameters, right? In the four input parameters, this, right? Like this, we can able to estimate the values for multiple dependent variables, so by using multiple independent variables. Now any doubts with respect to this? I am going somewhat fast because we are running out of time. I purely concentrated on the fundamentals or foundations of supervised learning. Now I am going somewhat quickly, because I assume that these machine learning mechanical engineering scenarios are known to all the participants, right? What is the minimum R square value to be considered? So the minimum R square, there is the thing is, if R square value is reaching 1, right, in terms of 0 to, the R square value has the interval 0 to 1, right? If R square value is moving towards 1, we can say that the model is performing well on the test portion of the data. Our model is predicting better values, right? If the R square value is towards 0, it is reducing towards 0, then model is not performing well or poorly performing, and the error will be high. The mean square error or the mean absolute error will be high, right? If R square is high, the
Sir?
yes.
Sir, what is the meaning of that adjusted R square?
Adjusted R square is simply the variant of this R square. It has a formula. This adjusted R square is generally used to more to more penalize the model in some situations, right? And this has a formula. These all things has formula. So in the interest of time, I am not talking about these things, remaining variables, right? We will understand over a period of time, right? Now quickly go to the next one. You see the plots like this. The plots are like this. The fuel efficiency, for the fuel efficiency, actual versus predicted values, if you plot, they are showing in somewhat a linear trend in the upward direction, right? Power output is also showing a linear trend in the upward direction, right? And these emissions are actually showing a linear trend in the upward direction. Now these emissions, if I see the interesting thing for emissions, you see the log likelihood value is -32, right? For the remaining two also, the log likelihood values are negative. So if the log likelihood values are negative and the quantity is high, this means the variable is actually performing better, right? Variable is actually performing better. Now, so this is residuals. The residual plot we have seen. Residual is nothing but the difference between training error and testing error, which we have actually formulated now. So this is shown how when you plot residuals, it should not show any pattern. The residuals should not show any pattern or any collinearity, right? So if the residuals show up any pattern or collinearity, then it is understood that the model is not performing well, right? It should not show any of these patterns. That is the most important thing, right? Any doubts here? Collinearity is I will answer that question. Collinearity means the attributes among themselves are said to be highly correlated in between independent variables. If the correlation value is high, then it is said to be multicollinearity, right? It is not depending on the predictor or dependent variable, right? So the correlation is in between independent variables itself. It should not be the case now. We are trying to find out the relation between dependent variable and independent variable, but multicollinearity, if it exists, then it means model is a fail. And for research work, what is the R square value to be considered, like 0.75 above or 0.85 above? There is you should actually compare with the past results for the same task at hand. If you are improving for something, then you should compare with the literature works, the results from the literature, and then you should come to a conclusion that your model value R square is better or not. Right, now continuing from here, then you should claim that yours is the better value. If it is new work, you should claim that this is the strength of the model and this is my value, right? And I cannot compare with the existing works. That is what you should tell, right? Now we have seen regression algorithms. Now we will see classification algorithms. So logistic regression, what I will do is I will stop here once I complete this logistic regression, and we will see the remaining two algorithms quickly when we come back, and we will start at 1:45 today. In the interest of completing these topics, we will join back at 1:45, and then we will complete the remaining two, and we will go to the lab session. Is it fine with all the participants?
Yes, sir.
Okay, fine. I will simply complete now this. Under classification, we are seeing three different algorithms. The first algorithm is logistic regression. Then we will see the probabilistic model, naive-bayes classifier, and then we will see k-nearest neighbors. Fine. So coming to the logistic regression, as the name itself is actually will make most of the people confusing, because until now you said different types of regressional techniques are there, like linear regression, multiple regression, and multivariate regression. Now why you are saying this logistic regression falls under classification, right? The name itself is actually making confusion, right? So it is not a regression model, rather it is a classifier, right? Logistic regression is a classifier, and it is binary and multi-class in nature. It supports both binary and multi-class classification problems, right? So here, as it is supporting the task of classification, it is not possible to use this as a regression function or regression method, right? So what this logistic regression does, it models the probability of a given instance in the form of and it models the probability of given instance, right? And associates that probability with the output label, right? Associates with that probability with the output label. And this logistic regression will finalize or the class level value based on the concept called maximum likelihood estimation, right? So this maximum likelihood estimation, what it does is it calls the max function and it determines which particular value or which particular class label is to be attached to this particular newly or unseen incoming unseen value or incoming unseen example, right? It uses maximum function, and it associates that particular class label for which particular class label the maximum value is obtained or maximum probability is obtained, strictly speaking. So that particular class label is assigned to that test example, right? So MLE says assign that class label for which the probability is high, right? Understood? So we are estimating the probability for the unseen example based on the concept of a likelihood, which internally talks about conditional probability, and says that if we are calculating the probabilities for the two class labels, two class data, for which particular class label the probability is high, assign that label to the unseen example, right? Now, so characteristics are like this. So it is a sigmoidal function, and it is most of the cases are used for most of the problems. We model it as binary classifier, and we also have a decision boundary which is plotted in the form of sigmoid function. And then we consider the heart of this entire discussion is MLE, maximum likelihood estimation, and we treat sometimes the decision boundary as a linear decision boundary, a roughly linear decision boundary, not a correct linear decision boundary, a roughly linear decision boundary. We also the logistic regression also supports what is called as regularization, so that overfitting can be avoided, right? So why we will talk about this regularization during our lab session. Then coming to the scenario considered here is predicting material fatigue failure, right? Predicting material fatigue failure when a material will have a fatigue, when a material is possessed with fatigue. Please tell me, when a material is possessed with fatigue, you can unmute yourself, or you can type it in the chat box. Because of dynamic forces, the material may possess fatigueness. And what are the other reasons? So you are seeing there are two particular attributes that are contributing to material fatigue. Those are cyclic loading and stress fluctuations, right? So yes, somebody said stress, right? And some people are saying that it is because of uneven loads, cracks, internal structure, yes, deflection. Yes, all these are the important what you say reasons with which the material fatigue is occurred, right? So here what we have considered is cyclic loading or uneven loading and stress on the material are the two primary factors which are actually making the material fatigue, right? So this, yes, all these answers are correct what you're typing. So now we consider these two factors, and we will try to predict the what you say class label for the unseen example, which is nothing but the likelihood of material fatigue failure through MLE, right? MLE is the thing that is actually getting executed internally in the logistic regression, right? Now, this information is actually critical for designing durable and safe mechanical systems, right? If material suddenly what is say becomes fatigue, then I doubt that material cannot be utilized for the longer period of time. It fails, right? So in order to predict such materials, we can use machine learning, and if it is predicted beforehand, then so much loss can be avoided, so much cost can be avoided, right? So you see this, the mathematical model for fatigue failure, right, for y is equal to 1, what we are doing is we are saying that the probability of material possessing fatigue failure is 1, and it does not has any fatigue failure, it is 0, right? So a binary classification. So it is a logistic regression, it is a sigmoidal function, right? The logistic regression uses sigmoidal function to do this. It is 1 by 1 plus e to the power of minus the f of x function. Now what is your f of x function? F of x function is a linear expression, right? Linear expression on the given set of variables. On the given set of variables, what are the two variables that we have considered here? For understanding, we have considered the cyclic load and stress, right? We substitute x1 for cyclic load and x2 for stress, and we will estimate the constant and the parameters b0, b1, and b2 with the help of a logistic regression technique, and we will come up with the accuracy of the model on the test portion of the data, right? So now this is nothing but the classification report. In this classification report, you are seeing precision, recall, and F1 score for the two class labels, right? So you see the number of records falling under fatigue failure is high. You see, support means the number of records under that particular class label, right? So under class label 1, there are 84 records, and under class label 0, there are 66 records, right? So the recall is high, the recall rate is high, and the precision is same. If you observe, the precision is same, but the recall rate is high for fatigue failure. It is because of the number of examples falling under that particular label, and obviously this logistic regression goes with this particular majority number of examples, leading to estimating fatigue failure is likely for the unseen material submitted for the sake of prediction, obtaining class level. Yes, sir. Yes, sir. We are going to now complete this. See this curve. This is a logistic curve. So you see the examples. This logistic curve is separating all the non-fatigue materials with all the fatigue materials. So all the fatigue materials are there at 1. All the instances with fatigue failure are presented at 1. All the instances that are not fatigue failure are presented at 0. And this logistic regression curve is a S-shaped curve which is separating these two set of examples clearly, right? The boundary is very clear. The logistic regression boundary is very clear, right? Any doubts regarding this? Yes, participants, if you have no doubts, then we will stop this session here and we'll continue from 1:45.
Participants, are you having any doubt?
If you have any doubts, please raise the doubts, or else we will simply stop the session now.
The next section begins at 1:45 p.m. Amma. It is not 2 o'clock, it is 1:45 p.m.
1:45, we will start this next session. Okay. Thank you. Thank you, sir.
Okay, okay, sir. Okay.
Okay.